I'm going to be working problem 218 from the SOA sample exam. This is a problem dealing with maximum likelihood estimation, and it involves censoring as well. So the problem gives you the survival function and two values of x that were observed, 2 and 4, and then it says that one other value exceeds 4. And then it asks to find the maximum likelihood estimate. So the likelihood formula of theta is the probability of all the observed values plugged into the density function. So it looks like that. So we need to find the density function first. We can find that f of x is equal to the negative derivative of the survival function. So we have derivative negative theta to the fourth times theta squared plus x squared quantity to the negative second. And that will equal 2 theta to the fourth times theta squared plus x squared quantity to the negative third times 2x. So we have that f of x equals 4x theta to the fourth over theta squared plus x squared quantity to the third. So now we can start writing out the likelihood function. It's going to equal f of 2 times f of 4 times s of 4. And this is because we know two observed values of 2 and 4, and then we were given that one other value exceeds 4. So we don't know its exact value, but we know that like it's at least 4, it's survived the 4, so we plug it into the survival function. So anytime like a problem comes out that says like some values exceed a certain number where they're censoring, you'll use the survival function like this. So we can plug those values into the density function and the survival function, and we get the likelihood function equals 8 theta to the fourth over theta squared plus 2 squared quantity to the third times 16 theta to the fourth over theta squared plus 4 squared quantity cubed times theta to the fourth theta squared plus 4 squared quantity squared. And if you simplify it, and that equals 128 theta to the fourth over theta squared plus 4 quantity cubed times theta squared plus 16 quantity to the fifth. Okay, now we're going to look for the maximum likelihood estimate. And to do that, we'll take the log likelihood function, which is just ln of the likelihood function. So we have that L of theta equals ln 128 plus 12 ln theta minus 3 ln of theta squared plus 4 minus 5 ln of theta squared plus 16. Now, since we want the maximum of this, we'll take the derivative and set it equal to 0, and that'll give us our the maximum likelihood estimate. So the derivative of the log likelihood function is 12 over theta minus 6 theta over theta squared plus 4 minus 10 theta over theta squared plus 16. And that is, when we set that equal to 0. Now if you simplify this some more, you end up getting that 0 is equal to negative 4 theta squared, or theta to the 4th, plus 104 theta squared plus 768, and yeah, that's equal to 0. Now we can find theta squared by using the quadratic formula, and the quadratic formula gives that theta squared equals 32. So theta is around 5.657. So 5.657 is the maximum likelihood estimate. That would be your answer.
So I'll be working SOA Sample Exam C number 37. We were given 3 sample claims, and that our claims follow a Pareto distribution with parameters theta equals 150 and alpha, and we're trying to find the maximum likelihood estimate for alpha. So our first step is to find the likelihood function, which is the product of the density functions evaluated at each of our sample claims. So we have the likelihood function is equal to alpha times 150 to the alpha divided by 225 plus 150 to the alpha plus 1 times alpha times 150 to the alpha divided by 525 plus 150 to the alpha plus 1 times alpha times 150 to the alpha divided by 950 plus 150 to the alpha plus 1. And you can simplify this to alpha cubed times 150 to the 3 alpha times 375 plus 675 plus times 675 times 1100 to the negative 1 minus alpha. And our next step is to find the log likelihood function, which is the natural log of the likelihood function. So we have that is equal to 3 natural log of alpha plus 3 alpha natural log of 150 plus negative 1 minus alpha times natural log of 375 times 675 times 1100. And our next step is to take the derivative of the log likelihood function. So we have that. This is 3 divided by alpha plus 3 natural log of 150 minus the natural log of 375 times 675 times 1100. And then we set this equal to 0 and solve for alpha, and we get that our maximum likelihood estimate for alpha is about 0.6798.
Okay, this is SOA sample number 61. It's modified a little bit. So the question is, you observe the following 5 ground-up losses from a data set truncated from below at 125. These are your 5 losses. You fit a ground-up exponential maximum likelihood estimation. Determine the fitted mean of the distribution. So basically, this 125 can be seen as a deductible, and the way you incorporate deductibles into maximum likelihood estimation is by standardizing it, by putting the probability that your losses will be above 125 into your distribution. So we're going to just recall that the PDF of an exponential distribution is 1 over theta, e to the negative x over theta, and the CDF is 1 minus e to the negative x over theta. Okay, so you first start off by your maximum likelihood estimation function, and that is your loss over 1 minus, and this is what I meant by standardizing, and then you do this for all your losses. And as you can see, this can be simplified by a lot. So the simplification becomes and you can even simplify this function even more, and it just ends up being 6. And that's just because you distribute this 5 out and then you subtract. And so now we'll need the log likelihood function, and that's just taking the ln of your likelihood function. And so you'll take the derivative of your likelihood function with respect to theta. And then you'll, by maximizing this, you'll set it equal to 0 and 0. And then find the value of theta at which it's maximized. So that turns out to be sorry, I forgot a negative sign. And so it's and then distribute that. I equals theta equals 82. And that's your answer.
So here's another problem from the SOA Sample Exam C number 44, which deals with MLE with data. So the problem is like, you're given losses follow an exponential distribution with mean theta, and the random sample of 20 losses is distributed as follows. And we have to find the MLE of theta. So the maximum likelihood function of, in this case, would be equal to the probability that 7 data did not survive within 0 to 1,000, and 6 data did not survive within 1,000 to 2,000, and then the survival function of 7 data above 2,000. And because this is a exponential distribution, we will get this, a function like this, with the mean theta. So we let P substitute this thing, and then we will get a less complicated equation with and simplifying it, we will get 1 minus P to 13 and P to the power of 20. So then we take the natural log of the maximum likelihood function, and then we will get negative 13 natural log of 1 minus P plus 20 of natural log P. And then we have to take the derivative of this. And then we will get negative 13 over 1 minus P plus 20 over P. And then setting it equal to 0, we will get over P equals to 13 over 1 minus P. And then we will get P equals to 20 over 33. So putting P back into this, we will get and rearranging the equation, we will get the maximum likelihood of the MLE of theta equaling to negative 1,000 over the natural log of 20 over 33, which is approximately equal to 1,996.90.